Hello, so this is my summary of motion graphs for A-level physics. You need to know about displacement time graphs, velocity time graphs and acceleration time graphs. We'll start with a displacement time graph. As an example here, we've got a journey where you should be able to spot that it started off going quite quickly, then stopped, and then travelled again relatively slowly compared to the initial speed. That should be stuff that you know already. What we need to know for A-level is, one, it's all about the gradients. The gradients or steepness of these lines tell you the velocity. That's simply because velocity is displacement over time, or the rate of change of displacement, and that's just what the gradient is. So this steeper gradient gives you a greater velocity. Here we've got a horizontal line, so zero velocity, and then compared to the first line, this line does not have as large a gradient and therefore you're travelling slower than the initial situation. But you do have to be careful about talking about things being fast or slow, as these are all relative and there's no scale on this graph, so you can really only make comparisons, so you need to be careful to use comparative language. The next thing that you're going to have to think about is how you would describe this line. Now, this line is a straight line, and if it's straight, you always want to include that it is constant. So, on a velocity time graph, the straight line would be a constant acceleration. On a displacement time graph, the straight line tells you that you're going at a constant velocity. There isn't that much else to talk about with this. What you might be asked to look at is a similar graph, and I'll just draw it underneath, but for something that's changing velocity. I'll just move that up slightly. So this is a displacement time graph again, but this time you might have a curve like this. And you just need to ask yourself what this shows. And if you ever get confused, always go back to yourself and say, well, what are the gradients showing me? I know that the gradient tells me the velocity. So here I've got a steeper gradient at first, changing to a smaller gradient at the end. So it's gone from fast to slow. So this is accelerating, but this is getting slower, so we'd normally refer to that as a deceleration or a negative acceleration. Similarly, you could have a curve that curves up like this, and then this time you can see that the gradient is increasing, so we would again say it's accelerating. One thing that you might get asked to do is, what is the velocity at a specific point on a curved line? And this is a skill that you'd have from maths, and you've probably met in the sciences lower down in school. You're going to come along with a straight edge and you're going to draw a tangent. Now you need to be very careful with your tangents, because if you look at my poor quality drawing here, I could probably argue that that was a tangent or that was a tangent. Really, if you do it carefully enough, there should only be one spot where you can just kiss the line. So there you go, I'm going to draw a line here, and this would be the line that I would use to calculate the gradient. And we want to draw a long line, so as long as possible. Not sure why I've written that down, but anyway, it needs to be as long as possible. And that way you can draw a large triangle when calculating your gradient. In another video I'll explain the importance of the large triangles. It's not something that's just made up, it is an important thing that we do. Okay, so what I might do now is look at a possible example of something you might be asked to do with displacement time graphs. And they might say something along the lines of, you've got a ball, and this ball starts off at rest and it's dropped. And I think that's pretty common sense. It starts with zero velocity, and then as it falls, the velocity is going to get larger and larger and larger. It's going to go faster and faster. It's going to accelerate. But you have to decide what is positive and what's negative. And the convention is, normally, that up is positive. So if this is falling down, it starts with an initial positive displacement, it's up in the air, and returns back down to the ground, to zero displacement. And then in terms of the velocity, well, the velocity is pointing downwards. It's getting increasingly negative, so we should end up with a negative velocity at the end. So what you'd sketch is something like, if I draw my axes, displacement, time, I need to show that it starts off with zero velocity. So I need to be careful at the start that my line that I draw starts initially horizontally, but it instantly has to start changing, because it doesn't wait a while and start falling, it starts falling instantly. So I'll start horizontally, but for a fraction of a millimetre, and then I will increase in velocity until I return back to zero, back to the ground. Now I haven't drawn this that well, that's okay now. Things you've got to look out for is that, one, it starts falling straight away. So you can't have a line that initially sort of heads upwards, because that would indicate that you've thrown the ball upwards. And you can't have a line that starts already with a gradient downwards, because that would indicate that you were throwing it downwards. It has, from the instant it's dropped, it would already have a velocity, a significant velocity. So you've got to be careful of that. And then you've also got to be careful what happens when you hit the ground, because I've got this line going vertically now, and remember the gradient is telling you how fast it's going, and a vertical line would be effectively an infinite velocity. So the gradient where it hits can't be vertical, and you need to avoid these little problems at the start here. And the other thing is, because this line's going down, we've achieved this negative gradient that we expected to indicate the velocity is getting increasingly large in the downward direction. Okay, now we've got velocity time graphs. I've sketched one here. Just like before, it's all about the gradients, and in fact this time we're also interested in the area underneath the graph. So, like before, these are straight lines that I've drawn here, so whatever's happening is a constant something. So here, well, the velocity stays the same, because it's a horizontal line, so that would be a constant velocity, which you need to contrast for yourself with what it looks like on a displacement time graph, because it would be a slanted line. And then we need to think about what the gradient actually tells us. So the gradient is basically going to tell us the rate of change of the velocity. So the gradient is v over t. And that's what acceleration is. So the gradient of our lines are going to be acceleration. And this would be a constant acceleration. Now, depending on the sort of question you're answering, you might be asked to work out the acceleration, or often they talk about things that are falling. And things that are falling, the acceleration, we know it because it's accelerating due to gravity. So we'll talk about that in a minute, but bear in mind sometimes from the question you can infer what the acceleration is going to be, and that would help you. Now the other bit of information that you can get from a velocity time graph is, well, if you work out the area between the line and the x-axis, that will tell you the distance you've travelled in that time period. Because distance is velocity times time, and that's basically what the area is. Now, there is a little catch here, so I'm just going to write area equals the distance travelled. Alright, alright distance. That should be okay, but it can sometimes catch you out when you have lines that cross the axes. So for example, I might sketch something like, so move up, something like this, velocity time. Got a T there. And this time you might be asked, well, what's the total distance travelled in this journey? And you just need to be careful that the area that we're talking about is the area that's enclosed by the line and the x-axis. So you would work out this area and this area and add them together. Now, the only other thing I'd like you to look out for with velocity time graphs is that for many instances it's about something falling. For example, a ball falling from rest. And in that case you will always know while it's falling, or while it's been thrown upwards as well, what the acceleration is. The acceleration is always going to be acting downwards to increase the velocity in a negative direction, so the acceleration is always going to equal minus 9.81 meters per second squared, or little g. Key thing to note there is the minus sign, so that will tell you about your gradient. And I'm going to go on to an example in the next video about balls being thrown up in the air and falling. So goodbye.